Okay, welcome to example 8. We have two gliders, glider A and glider B, on a frictionless track, so that way we can conserve momentum. They have spring bumpers, little springs here, so that when they collide with each other, that kinetic energy initially here is temporarily stored into elastic potential energy, but then it's redistributed back into A and B, not equally because they have different velocities, different masses, and then they go off with two different kinetic energies, but the sum of their kinetic energies before and afterwards are really the same, because this is an inelastic collision. And in elastic collisions, we have both momentum being conserved and kinetic energy being conserved. So there's no mechanical energy that is lost during this collision. So what we're trying to find is the velocity of A final afterwards and B final. We're going to have two equations and two unknowns essentially. So let's start off with momentum being conserved, because we know that this is a frictionless environment, so there's no external forces acting on the system. So we start off by writing momentum initially equals momentum finally. That's before and afterwards. To calculate the momentum before, we have two objects here, glider A and glider B. So that would be mass A, velocity A, initial, plus mass B and velocity B, initial, and then at the end we have mass A, velocity A final, and we have mass B and velocity B final. So let's go ahead and substitute the numbers. We have mass A is 0.5, velocity A initial is 2, mass B is 0.3, and velocity B initial is -2, and in the end we have mass A only given, so it's 0.5 times velocity A final, and mass B is 0.3 times velocity B final. So let's just clean this up a little bit. 2 times 0.5 is 1, and -2 times 0.3 is -0.6. So we're going to have 0.4 equals 0.5 VA final plus 0.3 VB final. So as you can see in here, we have two unknowns, VA final and VB final, and so we're going to have to probably use substitution. So what I think I'm going to do here is, it looks like if I multiply everything by 2 or divide everything by half, I can get rid of this 0.5. So I'm going to multiply the whole side here by 2 and this whole side by 2, and so I get 0.8 equals VA final plus 0.6 VB final. And so that way I can rewrite VA final is equal to 0.8 minus 0.6 VB final. And so it's ready to be substituted into some equation here. So we'll call that equation number 1. So now we need to find a second equation. Now I could use kinetic energy, but that's going to get a little bit messy algebraically, and so if you watch the video cast that I did on elastic collisions, you notice that there is this third neat equation that you can use that only applies for elastic collisions, head-on elastic collisions, and that is the relative velocity equation. So that's VA initially minus VB initially, so that'd be the sort of closing speed as they come towards each other, is equal to the negative of that relative velocity afterwards. That's VA final minus VB final. So let's substitute what we know. We know VA initial is 2, VB initial is -2, and so we get over here for VA final, we'll write that as negative VA final plus VB final. So over here we have 4 equals negative VA final plus VB final. And we should notice that we have two equations with two unknowns. And I'm just realizing I probably didn't need to multiply everything by 2 over here, because this was easier actually to put one variable by itself. But regardless of that, I'll write VA final equals VB final minus 4, and we'll equate these two equations. So we have 0.8 minus 0.6 VB final equals VB final minus 4. And so now we just do a little bit of math and figure out what VB final is. What you'll see is when you bring this over to the other side, you'll get 1.6 VB final equals 4.8, and that's going to give you VB final equals 3 meters per second. And then if we plug that back over here, VA final would be equal to 3 meters per second minus 4 meters per second. So VA final will be equal to negative 1 meter per second. So there's our two answers, here and here. So now let's take a look and show, maybe we're not really sure. We want to make sure that we did everything right. We want to show that this is a elastic collision. And to show that it's an elastic collision, what we want to do is show the total kinetic energy initially is equal to the total kinetic energy afterwards. So K initially is 1/2 mass A velocity A initial squared plus 1/2 mass B velocity B initial squared. So that's 1/2 times 0.5 times 2 squared plus 1/2 times 0.3 times negative 2 squared, and that's going to give you 1.6 joules. And so now let's go ahead and calculate kinetic energy finally. So that's 1/2 mass A velocity A final squared plus 1/2 mass B velocity B final squared. So that's equal to 1/2 times 0.5 times that velocity A final was negative 1 squared. And then we have 1/2 times 0.3 times 3 squared. And go ahead and calculate that. And voila, you've got the same thing. So since K initial equals K final, then it's elastic. Okay, and that's it for example number 8.